All right, let's go ahead and get started. Good afternoon, and thanks and welcome to our webinar, Learn How Sludge Gets Rid of Your Sludge, Augmented Aerobic Digestion with Nutrient Control and Case History. For those of you guys that don't know, our leader, one of our main leaders of our company, Jim Porteous, passed away last week, and I just want to dedicate this webinar to Jim. So, Jim, I know you're looking down on us from heaven. This is for you. But anyways, everybody, welcome, and we appreciate you guys taking time out of your busy schedules to listen to the webinar. This is one of the webinars we are planning on doing leading up to the WEP Biosolids Conference. This will demonstrate that an optimized aerobic digestion design can provide much value to a wastewater treatment plant. With improved aerobic digestion performance, not only can you save on disposal and O&M costs, but also help to improve the operation of other critical pieces of a wastewater treatment facility, such as the main treatment process and dewatering systems. So I hope no one has a cracked computer screen, because I'm not a very good looking guy, but I am Brian Wu. I am the group manager of the aerobic digestion department at Ovivo. I will be moderating the webinar. Just wanted to let you know that with the exception of myself and the panelists, you are all on mute. But although you are on mute, I encourage you to type your questions in the Q&A button. And as soon as you come up with a question, please feel free to type in that question as soon as possible, because I know, if you wait till the end, you might forget what your question is. My wife gives me a hard time that, I forget something that she told me like right away. So go ahead and type your question as it comes to mind. And at the end of the presentation, I will ask the speakers as many questions as possible. So I am deeply honored today to introduce our two outstanding speakers for this webinar. I will first introduce Dr. Glenn Diger. Dr. Diger is currently a professor of engineering practice at the University of Michigan. Go Blue! And he's also the president of One Water Solutions. He also worked for 35 years at CH2M Hill as a senior vice president and chief technology officer. He is a board certified environmental engineer, registered professional engineer, and distinguished member of the IWA. So welcome, Dr. Diger. Our other speaker is a good friend of mine that I've known for 11 years, Mr. Ed Petrosky. Ed has over 40 years of experience in the field of wastewater design, operations, construction, and administration. Ed is currently the executive director for Mountaintop Area Joint Sanitary Authority. He also worked as the director of technical services at NTech Engineering for over 13 years. He is a registered professional engineer in Pennsylvania and New York, and a licensed wastewater treatment operator. So please give it up for Ed Petrosky. So before we get started with the meat of the webinar, I would like to ask you our first poll question. So just to let you know, there will be 3 more poll questions through various parts of the webinar we will be asking. So please answer the following question. Why are you attending this webinar? Is it to gain knowledge on aerobic digestion fundamentals, to gain a better understanding on how to optimize an aerobic digester design, or to help improve operations of an aerobic digester? So I'll go ahead and launch the poll. And if you could, I would like, to get as many people as possible to participate. Please check which best applies to you, and I will post or share the results in about 30 seconds. So here are the results of the polls. Most of you, but pretty close, to gain knowledge of aerobic digestion fundamentals and to gain a better understanding on how to optimize an aerobic digestion design you're working on. So Dr. Diger, you got your work cut out for you. So now I'm going to turn it over to Dr. Glenn Diger, who will discuss basic aerobic digestion fundamentals and system operation strategies. And I hope, Dr. Diger, the coffee and soul is strong, because, I'm very grateful that, he spent this time this early in the morning in Korea. I think it's like 4 o'clock in the morning in Korea. So thank you, Dr. Diger.
I'm happy to be here. And this is a topic that's near and dear to me. It's what brought me involved with Ovivo in the very first, and it's a technology, aerobic digestion. It definitely has a place and can be highly beneficial. Again, as long as folks understand really just a few key things, and that is what we're going to be talking about here. So, aerobic digestion is simply where a process where we provide a limited supply of oxygen. It's really about controlling oxygen and controlling temperature are the key things here. And as we oxidize solids, as the bacteria oxidize the solids, they create heat. So by managing the oxygen and managing the heat, we can get an awful lot done with these processes, and in what is then from a mechanical perspective, something which is pretty simple. So let's go on to the next slide. So in terms of the microorganisms, we're using basically the organisms that we've grown in our biological treatment process. They're mesophilic, and this is important from a temperature perspective, that this is mesophilic refers to the temperature range over which they can and ideally function. So basically up to about 35 degrees centigrade. As you get beyond that, they're kind of like us, 35 degrees centigrade is getting up into, close to 100, and things get kind of miserable for us when the temperature gets that high. And in fact, you start to get beyond this, and the mesophilic organisms actually begin to die. This is the upper range for them. They can go down below it, but we have the ability to keep them at about 20 degrees or above, which helps to optimize their performance. Facultative, because they function with oxygen, but they're quite frankly, they can go for a period of time without oxygen and actually function for us under those conditions. So you want to put amount of air and transfer the oxygen that's needed, but not too much. So let's go on to the next slide then. So and again, what we're doing is in the activated sludge process, we're processing the organic matter and the influent wastewater, and we produce solids. In the aerobic digestion, then we are taking and converting those solids into carbon dioxide and water. Those poor plants there. That's kind of depressing, isn't it? But not what we do in the digester is not depressing. Next slide. So the science, there's good, firm science here. We'll go through it kind of step by step. The result, the last slide is the last equation that we'll show you is the important equation. But this is just to show you that when we know what's going on, and we know the fundamental basis for it, so it's not magic. So in digestion, what you see here is that we take biomass, we take bacteria and organic matter, and oxidize it to carbon dioxide and water. We actually make some alkalinity, some buffering capacity, and this becomes important because we're also going to make some acid, and we need the buffering capacity to keep a stable pH. On the other hand, the fact that we produce and consume alkalinity allows us, if we wish, to use pH as an indicator of what's happening in the process. Now, ammonium bicarbonate, ammonia, we with the conditions we have in the aerobic digester, we almost certainly will either have present and will grow nitrifying bacteria, which then take the ammonia, and this is the second equation, the ammonia, and convert that ammonia into an acid, nitric acid, which then at the pH that we have in the digester dissociates. So we've added acidity to the reactor through the nitrification process. The units are a little different here, but basically in digestion we create 1 unit of alkalinity. In nitrification we create 2 units of acidity. So if we just stop there, and this is a mistake that many people make, is they say, let's put more oxygen, more and more oxygen, and we just, you know, we digest and we nitrify, but we start creating acidity, and that actually starts to inhibit the digestion process. So if we just control the air and control the oxygen, we can digest. Well, and in the last equation there, you see the net result here of the net nitric acid that's produced. But if we denitrify, then we can recover some alkalinity and get us back to neutrality. So if we go on to the next slide, starting again with the digestion with nitrification, we're actually making nitrate, which can serve to do some of the denitrification for us. It can replace oxygen for some of the denitrification. So equation 5 shows that for the portion of the aerobic digestion, the portion of the digestion that we're doing using the nitrate that we formed, and what you see is that the biomass is converted into alkalinity. So we're actually producing alkalinity now, and then nitrogen gas. So we take the nitrogen gas, or the nitrogen from the biomass, and put it back into the atmosphere. So we actually get 2 things. One is it takes less oxygen to digest because we're using the nitrate that's formed, and we get some alkalinity back. So then if we look at the complete reaction, you can see how all of those things, which look pretty complicated, gets pretty simple. When we control the oxygen to nitrify and denitrify, less oxygen, because the nitrate that we formed does some of the work. We take the biomass, convert it into carbon dioxide and water, nitrogen gas, and there's no net consumption of alkalinity. Now, the tendency of the digester to become acidic and to inhibit digestion is eliminated by the simple step of saving some energy. It really is that simple. So let's go on to the next slide then.
Oh.
So, and because the reactions that are going on here produce and consume a buffering capacity, produce alkalinity, and produce acidity, we can actually, if we wish, use pH as an indicator of where we're at. Digestion produces alkalinity, 1 unit. Nitrification produces acidity, 2 units, denitrification produces 1 unit of alkalinity. So when we have these processes of digestion, nitrification, and denitrification in balance, we get a neutral pH that allows the digestion process to proceed well. But pH also tells us if the pH is going down, it tells us that we're allowing too much nitrification, or we're not allowing enough denitrification. So actually the dropping pH tells us to withhold some oxygen. So we have some indicators here to use from a process control. So it's really that simple. So I think, Brian, ready for the next poll question. So the question is, when designing or operating an aerobic digestion process, which common biosolids management concern is most critical to you? Biosolids management costs, side stream impacts of high total nitrogen and total phosphorus, energy costs, odors, dewaterability, meeting class B, and O&M issues. So I think we're ready for folks to tell us what their biggest issues are. I assume, Brian, that folks are checking and
Yep, they're still answering the poll. It took me a little while, Dr. Diger, to initiate the poll, but they're voting.
okay, good.
Got about 50% participation so far. We'll give it another 15 seconds or so.
Okay. So, and of course, with regard to one of these items, we've already also told you one of the benefits of saving energy by putting in the proper amount of oxygen is you actually are denitrifying. You're actually getting rid of the nitrogen that's the ammonia that's being released. So not getting too putting too much oxygen in, avoiding that produces a lot of benefits here.
Right. So it looks like based on the poll results, the top 3 are disposal cost, side stream impact of high total nitrogen and total phosphorus, and energy cost was the #1 concern. Yep, not surprised with an aerobic digester process.
Yep. So the things that we can look to do then from things that we control and so forth. So series or batch operation, that's about how we get efficiency through the system. Thickening is about how we can control temperature and manage the volume that we need. Aerobic and anoxic operation is about optimizing the digestion in terms of the extent of digestion, saving energy, and controlling the side streams. The combination of these things help us with temperature control and a little bit of physical side, and then the flexibility that how do we operate this? And Ed's going to talk through this, but it's actually a lot simpler than one would think. So this is the agenda for the next few slides. So next slide. Series or batch operation is about getting efficiency through the process. Many folks, and in years past, folks have just looked at, quite frankly, used aerobic digesters as just places to store sludge. But if we operate a batch process or a stage process, we get significantly more efficiency. This is something that we've known for a long time, but we can get the same job done in about half of the volume. That's the benefit here. So next slide, which is when we talk about a stage system, what do we mean? What we mean are tanks in series. So if you have a couple of digesters, rather than operate them with the same feeding and so forth into both of them, you feed into one and then go into the other. Pretty simple, but when you do something like that, you gain considerably, because these reactions, when you feed a digester at a higher rate, you get a higher rate of digestion. So in that first digester, you're getting a lot higher volumetric efficiency, because you're feeding it at a higher rate. So you essentially have a rougher and a polisher. The first one is where you're getting more of the work done because of the higher loading. Then as you go through into a second, or even if you have a third, that's where you polish and get and complete the digestion process, versus trying to polish only. That's how this operates. So next slide. Thickening, then, rather than thickening in the digester, thickening ahead of the digester allows us to have smaller digesters, but also is key to helping us control temperature, because you do produce a lot of heat through digestion, but the way you use that heat is to control how much water you're heating up. You put thin sludge into the digester, the heat that you're producing tries to heat up too much water. It's really that simple. So by thickening ahead, we have then the right amount of water to absorb the heat and to maintain the temperature. So, and as you see at the bottom, this makes a big difference in terms of meeting Class B requirements for pathogens. Helps us keep the size of the digester down. Next slide. Aerobic and anoxic operation. We've talked through the science of this now, so this allows us to control the nitrogen in the liquid. So this would control the nitrogen in any recycle stream. So we can essentially get 90+% control of nitrogen in any recycle stream that would come after the digester from thickening or dewatering. Preserves the alkalinity, so digestion continues more completely. Controls odors. It's okay to turn it off because you've got an oxygen source in the nitrate. So it's not that it's going to go septic. As long as you have a little bit of nitrate left, it's not going to go septic. Theoretically, you save 18% of the oxygen or energy because of less oxygen. And quite frankly, you save more than that because you're going to run at a low DO. You're actually going to save more energy than the oxygen savings because of that. So, so it becomes quite an energy efficient process. So these are the reasons that we look to do this. Next slide. So temperature control, it's about increasing the digestion rate. So again, we're going to destroy more of the solids, have less to manage. Gives us consistent operation year round. So we can do so we become much less dependent upon the ambient temperature in terms of managing the process. Allows us to maintain a healthy biomass. And what Ed is going to show you that, 20 degrees, which is really an ideal temperature, 20 or above, is very achievable, certainly above 15 as it indicates here. We do have to be careful to not let it get too high, and then we start killing our bugs. But controlling this is all within our capability. Next slide. So then the operational flexibility. So to do this, you really only have to monitor, pay attention to three things. One is the pH, because the pH helps us to tell us, are we, essentially, are we putting too much air in, or are we putting enough in? Because we produce alkalinity, but we also produce acidity. So the pH tells us the balance of those things. And as you saw with the equations, we want a balance of those two things. Temperature, so that we know that we're conserving enough temperature to get good, stable digestion, but avoiding excessive temperature. And dissolved oxygen. It's that easy, and from a control perspective. We control the sludge thickness then, which is about being able to control how much water is going into the process relative to the heat that's being produced, so that we control the temperature. And then the airflow is how we control the DO. Those are the things that if we pay attention to, have the right facilities, we can get a process that at a fairly modest amount of energy does an awful lot of work for us. And there was the question about phosphorus. In fact, what we find is that when we do this, we also can minimize the phosphorus release that's occurring. We can keep the phosphorus in the biosolids rather than them coming back around to the treatment plant as well. So Brian, I think that's about it, other than this polling question. Everybody get ready. But the question is, what do you feel are the strongest advantages of aerobic digestion? Relatively low capital cost, reduced side stream impact of high total nitrogen, total phosphorus compared to other biosolids management alternatives, operational simplicity, reduced odors, and ability to achieve Class B stabilization. So here we go. Tell us what you think.
We'll give everybody between 30 seconds and a minute to answer the poll question.
Someone is asking, when do we answer the poll question? It's now.
Yep.
Yep, someone's answering. It says it pops up as a prompt.
Huh. Okay. All right, I'll go ahead and share the results. So a lot of you like to KISS, keep it simple, stupid. Operational simplicity was #1, and everybody likes a bargain, relatively low capital costs. So those were the top two, I guess, advantages involved with aerobic digestion. So thank you, Dr. Diger. So now I'm going to turn over the keys to Ed Petrosky, who will present a series of augmented aerobic digestion case studies, which will discuss project background, design details, and operational results that were achieved. And these case studies will basically support the principles previously discussed by Dr. Diger. And take it away, Ed.
All right, thank you, Brian. Hopefully I'm going to bring some of the real world operational and construction and problem solving issues into this, so we can see how a lot of the things Dr. Diger was talking about are actually applied and can work, and you can see some benefits from this. I've got 4 projects to go overview here. They're mostly in Pennsylvania. You see the names. You can give me the next one, Brian. And this is just a map. Most of these are in Northeast Pennsylvania. The 2 up in the far northeast corner up on the Pocono Plateau, a little bit more cold weather issues up there. Next one, Brian. First one I want to talk about is Muncie, and what we were actually trying to do here was eliminate anaerobic digestion. It was a relatively small treatment plant, treating about 1 million gallons a day or less. There was a single-stage anaerobic digester. The equipment was worn out. They knew it was going to cost a lot to fix it, but the bottom line was they didn't get good digestion, and they were spending a fortune in natural gas trying to keep the thing at a temperature where it would anaerobically digest, and it was just bad all around. Next one, Brian. In the background here, you can see the round anaerobic digester that we that's already has a cover on it from the Vivo process. So we had a trickling filter you can see in the foreground. This particular plant generated a lot of solids. We had a bakery there operated by Kellogg's with 500 pounds a day of BOD. About half to 2/3 of the BOD coming into this plant were from this bakery. We had a very crude headworks. It was a manual bar rack, so a lot of stuff got through into the process. Of course, there were primary clarifiers, so a lot of it settled there, but that primary sludge went into these aerobic digesters. So a lot of the junk, if you will, got into the digesters. Next, Brian. So, the details were we converted this anaerobic digester using a draft tube diffuser. We also had an abandoned Imhoff tank from like 1950 on the site, and we converted that to an aerobic digester so we would get some more solids detention time, and we could do our series operation. Of course, it's a trickling filter plant, so there's no blowers on site, so we had to add some blowers. We had a little bit of issue with the Department of Environmental Protection insisting that we met a strict Class B design, which was part of the biosolids regs at the time, still is. So we changed our freeboard, we reduced it a little, and that abandoned Imhoff tank gave us enough detention time that we now had series operation and we met the requirements for time and temperature on Class B. Brian? Here's a picture of the converted anaerobic digester, and this is the draft tube aerator. And actually, this draft tube, and I got some better pictures later, it's my favorite. It does an excellent job. You can see the violence of the aeration and the mixing pattern it creates. It does a great job. Next, Brian. And this is the Imhoff tank with the cover on it. It was a square tank. We took out, those of you familiar with Imhoff tanks, we took out all those internal baffles, and we put a draft tube aerator in the center. Draft tubes work well on deep circular tanks or deep square tanks. When you start getting rectangular, better to shift to a shear tube type of diffuser, and we'll see some of them. Next. A little bit of operating data. Initially, 2003 was our first full operating year on it. We holding pretty decent solids retention times, good temperatures. In the cold season, never getting below 15.5. Dissolved oxygen, we didn't have any kind of automatic control, but the operators would keep it pretty low. But, at 0.3 and 0.5, we were still doing very good digestion. Volatile solids reduction, Class B says greater than 38%. We were measuring 69 to 84% volatile solids destruction in these digesters. Sour, standard oxygen uptake rate, another measurement to say, are you meeting Class B? The requirement being less than 1.5 milligrams per gram solids per hour. We're down in the 0.6 range, meeting that. Fecal coliform for Class B, we should be less than 2 million. In the cold season, we measured an 80,000 on this thing. Again, good performance. When we talk about the side streams, the decant from a digester, the filtrate from a dewatering operation, the ammonia numbers in this were impressive. It was something that we weren't even worried about when we designed it, but operationally, very low ammonia, very low nitrate nitrites, maintain this pH range with on-off cycling of the aerators. There was no alkalinity added to these digesters, and these are the alkalinity numbers we maintained. Next one, Brian. We went back and took some more look at the data in January through December 07. Again, 40 days solids detention, little trouble meeting minimum temperature in the primary digester, but in spite of that, we were still getting 77.8% volatile solids reduction, very low total ammonia numbers, low total nitrogen, excellent pH range, and again, just by cycling blowers on and off. And a metric that I like to keep, we took an average here. How many pounds of dry solids am I taking out of this place for every pound of BOD? I find that's the best metric I've come up with to look at our performance and success. 0.378 pounds of solids going out the gate, dry solids for every pound of BOD. 1 year we were as low as 0.27. And when you go back and look at 77.8% volatile reduction, those two numbers kind of bear each other out. The process really does destroy solids. Brian, next one. So in results, when we went back and measured, we reduced the amount of sludge to the landfill, biosolids, wet biosolids, by 50%. And that was a real number. That was off the scales at the landfill. We were meeting Class B. It was much easier for the operators to operate and maintain. And those diffusers, 13 years they were in operation, and they never clogged with a manual bar screen. This plant has since been decommissioned. It became part of a regional upgrade in the area. Pre-thickening, which to me is almost essential, but we did it here, but not by design. Again, trickling filter plant, primary, secondary clarifiers, daily wasting out of sludge pockets, you're wasting relatively thick sludge into these digesters. First summer we operated it. It was extremely hot that summer. We were well on our way to 35 degrees centigrade, had the hatches open to release heat. We started cycling the aeration 6 hours on and 6 hours off. That was the first summer it operated. They continued that cycle for 13 years. It gave the operator 6 hours of settling time to take some decant, thicken in the digesters, controlled the temperatures, and we had these excellent results. That's not only excellent results for denitrification, but it was excellent energy performance also. For 2 years, when this whole area regionalized into a new plant, this plant served as a regional sludge processing facilities because one of the other plants that was being eliminated just couldn't handle the biosolids load. So this plant was handling all its own and about half of the sludge load from another facility in these digesters. So it was a great success story for the community and for a project we did. Next one, Brian. I want to talk about Waymart. This is a plant that's up on the Pocono Plateau. We get nice cold winters up there. So that was a consideration. We were tripling the size of the treatment plant because the federal government decided they were going to build a prison up there. There was already a state prison in the community, which had its own treatment plant that had seen its day. So we had them abandon that plant. 3 facilities came into the community, so we had to triple the size of the plant. We decided on a sequential batch reactor, an SBR, which are notorious for the intermittent sludge wasting of very thin sludge. We wanted to produce a Class B, whether it be landfill or possible agricultural utilization, which Waymart had done up until that point. We wanted to minimize sludge production because if you do ag utilization, you only really get rid of it twice a year. If you go to the landfill, the nearest landfill is about 30 miles away. And of course, the wintertime operations, we had to conserve heat to make it work. Next one, Brian. And this is the digester system we built. It's a square tank, but it's really 2 tanks, so they're 2 rectangular tanks. We did not, and this is again another important thing, we did not screen our influent here as a cost-saving measure. We just used influent grinding to minimize solid size. So these digesters did get a lot of the trash from the wastewater, eventually ended up in the digesters. Next one, Brian. And these are the draft tube diffusers. This isn't a picture of Waymart, but it's exactly looks like the diffusers we put in there. These do very nicely in a rectangular tank. You can put them in a row across the tank. The drop pipe, the aeration pipe, is in that tube, and it acts as an airlift, bringing the sludge up through there in a pumping action, so you get excellent mixing right off the bottom, but yet your diffuser doesn't have to be down the bottom. This was another one. This was upgraded in 03. Yes, 03. And they still haven't clogged the diffuser up there, although they did recently put in screening last year. So it worked very well with these. It was a very good result using these diffusers in those tanks. And that tank that you saw in the picture, that was only the top third of the tank. About 2/3 of that tank is underground. Brian, next. Some of our operational data, the 04 was maybe a little early because I think we actually put the digesters online in something like January, February of 04. So that was partly why we had long solids retention time. We were filling. Temperatures we held good. Dissolved oxygens, not a lot of dissolved oxygen. That first year we got about 55% volatile reduction. The sour, a little higher than the requirement, but still pretty good. Fecal coliform, extremely low. Little bit of trouble for the operators maintaining that nitrification, but certainly some of those numbers indicate the ability to nitrify and denitrify, and later on they got a better handle on it. Pretty good pH range, again, not adding alkalinity to it. Brian, next. We went back, and these are small plants. The operators don't like to spend a lot of time analyzing, so we'd kind of go back and try and push them to get some operating data. So back in 06 through 07, 56 days average solids detention time. Temperatures dropping a little bit in the primary in the wintertime, coming back up in the secondary. Not quite as good, the fecal numbers, but still overall it was a Class B product. Still fighting a little with the ammonia and the nitrate, but there was the ability to control it, as you can see. pH range, pretty good. Dropping a little more in the secondary digester where maybe we're not cycling enough. And we get down to this pounds of dry solids disposed per pound of influent, BOD, and we're getting a 0.348. Again, an indicator that we're really breaking down a lot of the biological solids here and that we're getting that good digestion. Next one, Brian. So we met the Class B. We had excellent dewatering with a belt press, 18 to 22%. No odors. And in this particular plant, the digestion was so good, they operated the belt press once a week. They would fill about half a dumpster on a Wednesday, and then the next Wednesday, they would fill it the other half of the way. That cake was sitting in an indoor garage, and we weren't getting odors in a week, winter or summer. Sometimes that dumpster would sit there for 2 weeks and still not get odors out of that sludge. The diffusers still non-clog. The most recent average I calculated, 2013, 2014, 0.41 pounds dry solids per pound of BOD, still operating pretty good. Up in the prisons, they have a lot more prisoners. I sometimes say they're hot bunking up there. A lot of BOD coming into this plant and a lot of flow now. Next one, Brian. A little update. This past year, July 2016, we did an upgrade. We put an Ovivo membrane thickening system in there. That was to consistently put 3% sludge into the digesters. The manual system, which used these 3 old tanks, was just getting too labor intensive, not getting consistent thickening, and that was cutting down our solids detention time. The membrane allows us to get everything up to 3% or greater before it goes into that digester. Next slide, Brian. And this slide, this is an indicator of not only how good the digestion is, but when you're thickening with a membrane and taking all that water out through a membrane, you can get this excellent permeate to put back into your process. And this is something about the side stream loads. If you've got that requirement to have low nitrogen in your effluent, low phosphorus in your effluent, this is showing something. The red line is the ammonia concentrations. And when it gets down low, we're talking ammonia in this permeate that's less than 1 milligram per liter. Sometimes the process gets away from the operators. Mind you, they've just been running this. This data started in October, so they're still trying to get a handle on it, and they get right into the winter. Ammonia got away from them a little, made some adjustments, got the ammonia levels back down, started to get away from them in February, a couple more adjustments, and got it back down. Most of those adjustments had to do with not having quite enough dissolved oxygen, not enough aeration. Also, the brown line indicates the thickness. We tend to note that if we try and get it much above 3%, we lose our digestion because we're not getting the oxygen transferred. The other line on here that's critical is the blue line. And this is the phosphorus concentration in the recycle stream. Again, when the digestion is good, phosphorus levels of 2 and 3 milligrams per liter. Lose the digestion, it starts to come up a little. Started to come up in the winter. We made some adjustments and brought it right back down here in February and March, that we're getting these low levels of, less 2 milligrams per liter, or 2 to 2.2, 2.4, just ridiculously low levels of phosphate in that recycle stream. Just does an excellent job on that. And again, it's not just the membrane. You have to have the digestion working correctly also. So again, it shows with operator attention. These are good operators, but again, they're learning a process. But with operator attention, paying attention to the details, you can get excellent side stream quality. Next one, Brian. Okay, so we got a little polling question here. If you operate an aerobic digester, what is your biggest challenge? The lack of volatile solids reduction, managing that total nitrogen and total phosphorus in either your decant or a side stream flow? Do you have hydraulic issues? Not enough detention time in there? Do you have reduced capacity? Or do you, is it the high O&M costs, such as the energy, the disposal costs, or the maintenance? So Brian will let us know when we start getting some answers in, but I guess he'll allow about another 30 seconds, so get them in.
Yep. We got about 30%, and I just want to let you guys know that if you could answer them live, that'd be great, because once we initiate the poll and we end the poll, that's really your only opportunity to answer the poll. We'll give you about another 10 more seconds. And here are the results. It looks like high O&M costs, such as energy, disposal, and maintenance are the top ones. And then it looks like the managing the total nitrogen and phosphorus, as well as lack of volatile solids reduction, seem to be the other challenges. So thank you for answering the poll.
All right. Again, I think I've touched on some of those issues in the prior slides, and I'm going to touch on it again as I go through these other ones. Project we did in Frackville, I call it the energy efficient time saver. We had a situation in this plant where the operators were operating their dewatering equipment probably on the order of 50 to 55 hours a week. Now, This is a plant. It's not a large plant. It's about a 1.4 million gallon a day plant. The operators are typically working an 8-hour shift Monday through Friday, not operating it around the clock. So once we started operating the press over 40 hours, that became a concern. We were in there at night. We were in there on weekends. Of course, it's a concern for the authority because they're paying overtime. So the operator said, well, the answer is we need a bigger belt filter press. I said, you really want to reduce your dewatering time. Why don't we try and reduce the biosolids through volatile solids destruction? Now, at this point, I had probably already done about 6 of these projects, and I knew what could be done. And I also knew we could reduce the energy. So the next one, Brian. So again, it's an SBR. So we have this, thin waste stream, lots of it, intermittent pumping of the sludge, wasting. This plant had a specific phosphorus limit, and they were adding ferric chloride to the process to control the phosphorus so it would settle out when the digesters would go into their settle phase. Or not the digesters, when the SBRs would go into their settle phase. Open top aerobic digesters with coarse bubble diffusers on the tank bottom. Again, a belt filter press. The biosolids were going to a land reclamation facility, an old strip mine in Schuylkill County, Pennsylvania. So the disposal cost was low. It wasn't even very far to truck it from this treatment plant. But they had to add hydrated lime, and they used 50-pound bags to try and achieve a Class A sludge for the land reclamation project. Next one, Brian. We covered the digesters, and again, the shear tube diffusers, because these were rectangular tanks, and they worked well in this configuration. The other thing about these diffusers is, as you look at that black tube, the draft tube, which acts as the airlift pump, the diffuser is not at the bottom of that tube. It's about halfway up that tube. The diffuser is not at the bottom of the tank. We reduced the back pressure on the blowers significantly by not having the diffuser at the bottom of the tank. But by sending the draft tube down to the bottom, we're pulling the sludge off the bottom. So we're getting the thorough mixing all the way down to the bottom, and we're pulling this sludge at high velocity past the diffuser, and that's causing the bubbles to shear and be more of a medium bubble size, if you will. So that's the diffuser setup in here. We also went with high efficiency blowers on VFDs to get our best bang for the buck in how we're getting the air. The only thing we did with the belt filter press was we gave them a new sludge conveyor. We did not change anything on the belt filter press. It was in good shape. Next one, Brian. And this is a picture from the top with the aluminum covers in place, the air distribution piping on top, and all those little black dots you see there by that air piping, that's the access to the diffuser. So even if you're completely filled with sludge and you happen to clog one of them, open up the top. It's just like cleaning out a gun barrel. Put the top back on and you're in operation. So you don't have to drain the whole process. You actually don't even have to shut the process down. Next one, Brian. This is the before and after. Before we put the air beam system in there, the covers, the diffusers, the purple bars indicate how much solids were going out of that facility every month. After we did the project, the red line is what happened. That's how much every month we were reducing the solids compared to prior years. The loads in the plant were the same. It's a small little community with a state prison discharging all its wastewater into it. So again, it's a pretty consistent flow, and there's not a lot of growth or drop off in growth. So the results over the years, nothing has changed that much in the plant except the sludge quantities. Next one, Brian. So we reduced the sludge going out the door by 57%. Now it's a $17,000 annual savings, but again, it's going to this reclamation site at about $20 a ton tipping fee. If that would have been going to a landfill, the savings probably would have been about 3 times as much. Our local power utility, PP&L, gave us an energy rebate of $27,000 one-time payment for cutting back energy. The annual energy savings compared to the prior system were $18,000 a year. And these digesters had their own blower. So that wasn't a guesstimate. That was measured by PP&L, independent third party, if you will. So again, those energy savings are real and verified by another outfit. Chemical savings, well, if you cut the sludge by 57%, you cut the bags of lime by 57%. The operators loved me for that one. We cut polymer into dewatering. Here's the other one. We don't measure the phosphorus, but I know it went down. The operators started reporting lower phosphorus in the effluent. So they started cutting back on the amount of ferric after we did this digestion project. Ultimately, they stopped adding ferric chloride for phosphorus removal, and the plant typically gets phosphorus levels of about 0.5 milligrams per liter or less. In the past, they were adding ferric and getting something around a 1, a 1.1, a 1.2. All a function of aerobic, anaerobic recycling. And as Dr. Geiger can tell you, he's helped write some of the papers, you can see a 50% reduction of that phosphorus in the side streams if you go to aerobic, anaerobic cycling. I've seen it in other situations. Here, it was a very graphic example when we totally stopped using ferric chloride. Reduced the manpower, that 50 to 55 hours of sludge dewatering became 25 hours. So instead of putting the money into a bigger press, we put the money into better digestion. Dry solids, 2-year average, 0.36 pounds of solids per pound of BOD. Next one, Brian. Central Wayne, up in Wayne County, Pennsylvania, they had a consent order. They had to build a new plant. We had to build a bigger plant. We chose to build a 2.2 million gallon per day sequential batch reactor. Next slide, Brian. The old plant had been a primary clarifier, trickling filters, straight secondary limits. They had existing aerobic digesters that in 1990 had been converted from anaerobic digesters to aerobic. But it wasn't a very efficient design. They weren't covered. They were small little rubber membrane diffusers on the bottom of the tank, a lot of back pressure, just didn't work real great. There was an existing belt filter press that was almost 20 years old. They didn't have any real sludge issues, but again, straight secondary limits, not really removing a lot of material from the wastewater. Next one, Brian. We upgraded to a 2.2 million gallon a day sequential batch reactor. We had much stricter effluent limits. We had an SBR with the thin wasting, so we just ended up with more biosolids. We took an old clarifier and we converted it to a sludge holding tank. That allowed us to equalize the sludge wasting from the SBR. We had some telescopic valves there that they could do some minimal thickening of it, but we got a new belt filter press, triple decker with a gravity drainage belt on top, and that allowed us to significantly thicken the solids that were going into the aerobic digesters. Next one, Brian. So we covered them with the Ovivo air beam. We used the draft tube diffuser, and our thickening, we were wasting 5 to 6% solids into this digester to increase our solids detention time. And we actually did the calculation backwards. We figured, how thick did we have to make the solids to only need 2 digester tanks instead of building a third one? That's why we were wasting at 5 to 6% solids. Next one, Brian. This is a picture of the old clarifier that we fixed up and converted into a sludge holding tank. And those are actually Ovivo Transmax diffusers in there, just because they're so resistant to clogging. The next one. And this is the digester, originally built in 1955. Did a lot of cleanup, paint up, fix up on the building, but kind of the architects maintained the 1955 style. And you can see the aluminum covers on top, which were they're really putting a cover on the pot when you're trying to boil the water. We're holding the heat in. Next one, Brian. That's the draft tube diffuser. That is quite long. That's about 30 feet in length. The draft tube is about 4 foot diameter. And I think this one had about 8 drop pipes in it for the diffusers. Next one, Brian. And there it is sitting in this old circular digester. Next, Brian. And cross section of this tank, this was a 30-foot deep tank with the draft tube in the center, cover on top. The bottom of the diffuser is 7 feet off the bottom of the tank. That goes to some of your energy savings. We're not pushing air against 30 feet of water. We're pushing it against 23 feet of water. That back pressure is a significant savings. But again, the bottom, and it's a little hard to tell, the bottom of that draft tube is 2 feet off the bottom. It's still pulling the sludge from the bottom, giving you this large velocity in the center, carrying your air, transferring your oxygen, and creating a mixing pattern. Next one, Brian. And this is the cover being put in place during construction. Next, Brian. And the results, Class B, easier to maintain. 5 years, we haven't clogged the diffuser. Good 5% solids to the primary digester. Volatile solids reduction to 77%, and about 0.34 pounds of solids per pound of BOD. Brian, next one. And this is the last one. You don't have to listen to me anymore after this. We got our Class B performance, excellent volatile solids reduction. We got the energy savings. We got the ease of operation, non-clogged diffusers. These things haven't been drained in 5 years. We get excellent wintertime operation. We maintain our operation. We have low nitrogen and phosphorus limits, and the quality decant from when we dewater and when we thicken just gives us low nitrogen and phosphorus that we don't have to be taking it back out again in the SBR. And I think as you saw through all of these, it's always an easy retrofit no matter what our tank configuration is. And most of these that I showed you were done on existing tanks. I think Waymart was the only purpose-built digester in these 4 examples. So with that, I'm done. Thank you for your attention. I appreciate it.
Okay, thank you, Ed, and thank you, Dr. Diger. And I just want to let you know before we begin the Q&A session, I want to make sure everyone is aware that a copy of this presentation will be available at the utilitiesofthefuture.com website. So I'll go ahead and start the Q&A session. I guess I don't know if Dr. Diger or Ed wants to answer this question, but what is the ideal thickened solids concentration coming into a digester?
So I'll start. So one of the things I often say is the way you know when you're talking to an expert is the answer to every question is it depends. So it depends. But I think what you find is that for the systems, for the kinds of outcomes that we're talking about here, you're probably talking about something generally in the 3 to 4 to 5%. When I say it depends on how much digestion you can get out of the sludge, meaning how digestible it is, so therefore how much heat is produced relative to the amount of water. The thickness is telling you how much heat can be produced relative to the water you have, right? The thicker it is, the more heat you can produce relative to the water, and the thinner, the less heat, and therefore the relative to the water. So that's one factor. Then the other is how good the insulation. So Ed was showing you that, covers, and anytime you're into a cold environment, you're going to have covers, but also the amount of insulation around the tank itself, whether it's mostly concrete, but certainly if it's buried versus above ground affects the insulation. So those are the things where it depends on. You also you can get to the point where the sludge is so thick that it becomes difficult to transfer the oxygen, and Ed really referred to that as well. But even if you're feeding 3 or 4%, 5%, but it's very digestible, the solids concentration in the digester, then I think that what you would find is that if the solids concentration in the digester is no more than about 2 or 2.5%, so this is after digestion, but if you're no more than about 2 or 2.5%, you can mix it then, and the oxygen transfer is just fine. One more thing is that when you're feeding sludge this thick, and even after digestion, mixing is not an issue because not much is going to settle. It's thick enough that you're not going to get much settling. So you can, as Ed was saying, you can turn the air off for some time and you really don't get much settling just because the sludge is pretty thick. Ed, anything to add to that?
Yeah, and one of the things I look at is, and I've done quite a few of these plants and there's people out there with colder regions, but we get our fair share of cold up here. And I look at all the water that you take out with the thickening as ice cubes in your cold drink. Particularly in the winter, we have SBRs up here operating at 7 and 8 degrees centigrade. I want a digester operating at a minimum of 15. If I put all that 7 and 8 degrees centigrade water in there, I'm going to cool that thing off. I want to take that water out before I put it in the digester. So that's one of the key things with me, maintaining temperature in the wintertime. That's part of what the pre-thickening is. Also, the other thing is, and I think Central Wayne was a good example of that, we had an extremely tight site. We were wedged between a railroad track and a river. We didn't have a lot of room. I did not want to build another digester. I didn't have room for another digester. So I said, how thick do we have to make it in order to not build another tank? And the answer came back 5 to 6%. So we designed our system so we could put 5 to 6% sludge in the primary digester. Now, the digester is burning it up like crazy. And as Dr. Diger showed in his equations, most of what you're converting it to is water. So even though we're putting in 5 and 6%, the digester is probably operating at around 2.5 to 3%. So again, thicken it, be able to handle that thick sludge. Don't think you're going to pump it with some lousy centrifugal pump that isn't designed for it. You're going to have to be using some positive displacement pumps. But again, design for it, do it. Your process will work, and you'll get the benefits in the long run.
Okay. Thanks, Ed. Thanks, Dr. Diger. Next question, which I think is a really good one. I think, Ed, maybe I'll direct this question over to you first. Why no ORP measurement in the digesters? Are there any advantages of DO over ORP?
I think the advantage of ORP over DO is I think it's a more robust probe for sticking in 3% sludge than a DO probe. But here's the other side of the coin. I'm doing some of these at smaller plants, and we're trying to stay on a budget as much as we can. Instrumentation can add a lot of money. But this isn't a fast process. This isn't a process that's turning over every couple of hours. This is a process with a 45-day detention time. You go out there and measure the DO on Monday and keep your conditions kind of the same, you don't have to go checking it every 4 or 5 hours. You check it once or twice a week, and it probably isn't changing. So the trade-off, in my mind, with the instrumentation at some of these smaller plants is check it periodically to make sure your air settings, you're putting enough in. You don't have to have a process monitor telling you constantly what the DO or ORP is. Again, it's a slow moving process. So I look at it as tell the operator to check it, and we don't have to spend a lot of money not only buying and installing probes, but maintaining them. So that's kind of where I'm at with it. I think the process is simple enough to operate it that way.
Thank you, Ed. Dr. Diger, I think you would be the best person to answer this question. How do you control the nitrogen and phosphorus released from the biomass decay in the aerobic digester to a low level?
So let me separate it into the nitrogen and then the phosphorus. For the nitrogen, the simple answer is that you control the released nitrogen by converting it into nitrogen gas. So, as the digestion process, as the solids are destroyed, you're releasing ammonia. But what we do by controlling the aeration, as Ed has just really described, is we create conditions where nitrification can occur, but also then we use that nitrate to do some of our work, to denitrify, and it converts it into nitrogen gas. This would be exactly what we're doing if that's recycled into the mainstream. The thing is, in the mainstream, a lot of times we don't, we're kind of shy on carbon to get all the denitrification. Here we're taking that nitrogen, and we're actually using it to do the nitrate that we form. We're actually using it to do some of our work. We're using it to do some of the digestion. So so we're getting benefit out of it rather than creating a problem for ourselves with the recycle stream. Phosphorus, and as Ed showed in that one example, what we find is that yes, you get release. If you have biological phosphorus removal, you get release, but by controlling the oxygen, you also get uptake. So that's pretty universal observation. So by controlling the aeration, and not the thing which will surprise folks, but not over aerating, you actually not only get release, but you get uptake and keep the phosphorus in the biosolids. So from an overall perspective, what happens to the nitrogen? Well, it goes back into the atmosphere, which is where it came from. The phosphorus stays in the biosolids, but it stays there rather than come back around to you again.
Thank you, Dr. Diger. Ed, this question's for you. For any of your plants that you presented, do you need to do supernating, or is there no need? And are there any odor emissions during decanting and supernating?
Okay. Boy, I got a bunch of answers there for that. These plants have a range of do we or don't we decant. The Central Wayne one, for example, where we're going in at 6%, there's no decanting in the digesters going on because it's probably coming out of the digester at 2.5%, and that's just not going to thicken anymore with gravity. The Muncie one, they were doing some decanting of the digesters. They would get some water off it. In Frackville, they're putting the thin SBR sludge in. They had a limited budget. There was not enough money to do pre-thickening. Operators, being the, necessity is the mother of invention, and operators are right on the top of the list there. The operator takes dry polymer about twice a week, throws it in his digester, turns on the air, lets it aerate and mix, shuts off the air, and lets it settle and pulls off his decant. So he's actually doing his thickening in the primary digester, and it all works. In terms of odors, I tell all the operators, once a day, you got to shut it off for at least 4 hours. No air. That's going to let it go anoxic, take care of your denite. It's going to go anaerobic, help you with your phosphorus release, and then turn it back on. maybe you can go 5 hours, maybe you can go 6 hours. It generally doesn't create odors if you do it in that time. I had one operator who said to me, "Oh, it stunk like hell." I said, "Well, how long did you leave it off? 6, 7 hours?" He goes, "No, it was a little longer than that." I said, 8? He said, "Well, actually, it was 16. Yeah, you leave an aerobic digester off for 16 hours, it's going to stink when you turn it back on. But if you stick to 4, 5, 6, 7 hours, you're not going to get any odors. As Dr. Diger said, you got the nitrate, the NO2 in there, the NO3, you got your oxygen source that it's using. So my personal experience is 4, 5, 6, 7, 8 hours, probably not any odors. You go beyond that, now you're going to start getting odors. How's that sound?
That sounds great, Ed. And Dr. Diker, one more question for you. Is there a rule of thumb when aerobic digestion is more cost effective than anaerobic based on plant capacity in MGD?
The old rule of thumb is the break point between anaerobic digestion and aerobic digestion. The old rule of thumb is about 10 mgd. And energy prices are going to be a big in that. So I would say that's if you're down to 5 mgd, you might pencil it out a little bit. You get it much above 10 mgd, and anaerobic digestion is probably there, but that's the general magnitude of it.
And I would kind of concur with that, but I think, and this is my advantage on some of the projects I have in northeastern Pennsylvania, our energy prices are very good, very low. So we can afford to run the blowers. But I also think a lot of people still have a lot of misconceptions about aerobic digestion. And I think when we start doing it this way, when we start putting covers on it, using efficient diffusers, non-clogged diffusers, I think we might actually, and the very clean side streams, I think we might be able to actually expand that into larger plants and still be economical. Now, no, if you're in an area where your cost of energy is extremely high, then it's probably not. But if you have a reasonably good cost of energy, I think this process can work at larger facilities.
Yeah, I agree.
Thanks, guys. And last question, and this is for Ed. For the Frackville plant, what were they using for aeration before you installed the shear tubes?
I hate to say anything by brand name. We were using the stainless steel tube diffusers. They're 18 to 24 inches long. They have the large holes on them. That's what was in there. And they were very close to the bottom of the tank, probably 6 inches off the floor. Just a lot of clogging issues with them, so you're not getting your good aeration. Then you're draining your tank to go in and clean them. So that's what was there before. The Ovivo, I got to hand it to you guys. You got the design down on a sludge digester diffuser. They just don't clog. And you can clean them out if they do, but I can't tell you I know anybody that's ever had to open up that top and clean it out because they don't clog in the first place. But that's what was there. And I've taken those kind of diffusers out of a couple digesters and been much better off without them.
Thank you, Ed. And there were quite a bit of questions, and we weren't able to get through them all. I know, Dr. Diger, you got to catch your flight back home to the U.S., so safe travels, Dr. Diger. This will conclude our webinar, and I would like to again thank our speakers, Ed Petrosky and Dr. Glenn Diger. You guys did a fantastic job. And again, if you guys want a copy of the presentation, it will be available through the utilitiesofthefuture.com website. CEUs will be provided, and I believe information on how to receive the CEUs will be available through the utilitiesofthefuture.com website as well. And again, thanks for all that attended, and have a great Friday.
Thank you. Everyone take care.
Yeah, Good Friday to everybody.